Welcome back to G Fun Facts Online, your go-to source for mind-bending science and the tech of tomorrow. I am your host, and today we're diving deep, really deep, down to the atomic level to talk about something that sounds like a mistake, but is actually a revolutionary design principle: atomic vacancy engineering. Imagine building with Legos, but instead of just putting bricks together, you're carefully deciding which bricks to leave out. That missing brick, that tiny empty space, changes everything about your Lego creation. In the world of material science, that missing brick is a missing atom, an atomic vacancy, and engineers are learning to control these vacancies with incredible precision to create next-generation electronic devices. This isn't about imperfections. It's about intentional, meticulously tuned defects that unlock amazing new properties in materials. Think of it as less is more, but at the atomic scale. Recent breakthroughs have really put atomic vacancy engineering in the spotlight, especially with super-thin, two-dimensional materials. You might have heard of graphene? Well, there's a whole family called transition metal dichalcogenides, or TMDCs for short. These materials are just a few atoms thick, and in these ultra-thin sheets, even a small number of intentionally missing atoms can dramatically change how they behave. We're talking about creating specific electronic and optical quantum states, basically using these tiny empty spots as quantum antidotes. This is paving the way for some seriously futuristic quantum devices. One of the most exciting applications is in thermoelectric devices. These are gadgets that can convert heat directly into electrical energy, or vice versa. Scientists have figured out how to use vacancy engineering in semiconductor alloys, complex mixtures like silver, copper, tellurium, selenium, sulfur, to make them way better at this heat-to-electricity conversion. Not only that, but these engineered materials are also more mechanically flexible. Picture this: self-powered wearable electronics that run on your own body heat. No more dead smartwatch batteries during your run. This could be a game changer, significantly cutting down our reliance on traditional batteries. But the cool applications don't stop there. Vacancy engineering is also a big deal for developing advanced sensors and catalysts. When you remove an atom, the spot it leaves behind can become a super active site for chemical reactions. This can massively boost the efficiency of things like hydrogen evolution, a key process for clean energy. In electronics, those missing atoms can tweak how many charge carriers are available and how easily they can move through a semiconductor. These are crucial factors for designing better transistors and all sorts of electronic components. For example, researchers are strategically creating vacancies in materials like molybdenum disulfide, or MOS2, to enhance its performance in energy devices, specifically in something called triiodide reduction. Now, creating these missing atoms with pinpoint accuracy is, as you can imagine, a huge challenge. We're talking about manipulating individual atoms here, but scientists are developing incredibly sophisticated methods. Techniques like thermal annealing, basically carefully heating materials, and controlled vapor deposition are being refined to create vacancies with atomic precision. And to see what they've done, they use tools like scanning tunneling microscopy, or STM, which can literally image individual atoms. Combine that with powerful computer simulations based on first principles calculations, and researchers get a deep understanding of these engineered defects, even down to how a single missing atom affects its local environment. Looking ahead, the biggest hurdle is figuring out how to mass-produce these vacancy-engineered materials efficiently and scalably so they can be used in everyday technologies. It's one thing to make a tiny sample in a lab, but another to make enough for widespread industrial use. However, there's a lot of promising research. For example, a technique called the 2D Czochralski method is being explored for making high-quality 2D semiconductor materials, which could be a big step forward. The field is constantly evolving, with new synthesis methods, better characterization tools, and more powerful theoretical models. The ability to clearly link the 3D structure of these atomic defects with the material's electronic properties is going to be key to designing materials with custom-tailored functions for advanced electronics and quantum computers. And the applications keep expanding. Scientists are now exploring vacancy engineering for next-generation memory technologies and even neuromorphic computing, which aims to create computer chips that work like the human brain. So, next time you think about materials, remember that sometimes what's missing is just as important, if not more so, than what's there. Atomic vacancy engineering is showing us that a little bit of nothing can lead to a whole lot of something amazing. That's all for today on G Fun Facts Online. Join us next time as we explore another fascinating corner of science and technology. Stay curious.